Okay, sir.
Okay, so let's start the class 3, and maybe by class 4 I'll be finishing up the basic part of it, the basic part of this theory. Then the last two classes are going to be depending upon if the students want to discuss up any particular thing theoretically, because I'm actually a physicist. I'm a theoretician on NMR spectroscopy. I'm not a chemist or biologist, that I cannot talk about much of this application of NMR, for which you have the entire course left. So application, but if for example students want a particular concept to be discussed again, that can be done. Otherwise, I can go a little deeper than whatever I'll be doing by next class. So by today and by next class, I think tomorrow, most of the structure, the basic structure of NMR theoretically will be done. Then I'll go a little deeper. If suppose somebody wants to know a basic concepts of say 2D, where from the 2D is coming, or something else, I can do that as well. It's not a big deal. So let's start this one. As usual, I always start with a little bit of a recap of whatever has been done. So we had seen so far, and this particular app is another good thing is that I can use this laser pointer. You can see this laser pointer, correct? So this is another good thing of this particular app that I was talking about. I can toggle between pen. I can write pen, or I can toggle between laser pointer like this. That's the thing. Anyway, so whatever we have done so far is we have seen this nucleus with non-zero spin or NMR active. That means we call it I. I is non-zero, and then this is we have seen too many times these two equations, the value of I and the Z component. Last class primarily we had seen this particular scene, that if now we keep a particular nucleus which has non-zero spin inside a magnetic field, what will happen? Two things will happen, which we have covered in last class. Very quickly I'll go through them, just reminding you. One is Larmor precision, and this Larmor precision is going to come from the torque that is going to be applied on the spin. And we have proved rigorously last time that this particular torque is going to make this particular tip of this vector precise. Let me expand this picture a little bit for you. So this tip of the thing will be precise like this, and the precision frequency is going to be given by this. So this is called a Larmor precision frequency, and this Larmor precision frequency is proportional to gamma at a particular magnetic field. So even if we have a fixed magnetic field, that is going to be the case for any particular spectrometer. Suppose you have taken a 400 mega spectrometer or a 700 mega spectrometer, the main magnetic field B, the strength of the main magnetic field is fixed. You cannot change that. Earlier, when it used to be electromagnets, lower magnetic field NMR machines, then that time it was easy to change that B, but now it is not possible. Once it is installed, B is fixed. So therefore, the Larmor frequency now is entirely dependent on this gamma, and we have seen that the gamma has this particular unit, per second per Tesla, or Coulomb per kg, that is equivalent. I have proved that, or Hertz per Tesla. And also we have proved last class that for proton, an isolated proton, the omega at 1 Tesla magnetic field is 42.58 megahertz. We calculated that. So I have just taken a table from internet, which shows basically for the proton the same thing, which is 42.58 equal. This is the same thing, 42.58. And then it has other few nuclei which are very popular in NMR, and their frequencies are given as well. This is all for, this is megahertz per Tesla. So if for 1 Tesla, it is exactly this amount. But if we increase the Tesla up to anything, then it is going to be changed. One good thing that we can see from this table directly is if we look at this carbon 13 here, this carbon 13, and if we just take this proton, I can clearly see that these two are kind of 1/4. So we have about 42.57 and it's 10.7. If we just multiply it by 4, it is going to be very close to this. So that means the gamma of carbon is 1/4. This is something also I told last class. Now in number you can see that. And another thing that I told is N15, and that is 1/10. I can clearly see that this is 4.3 or it's 42. It is nearly 1. This is 110. So obviously, as we have this particular gamma being changed, so therefore we have a different, for a particular B, we have different alarm frequency. So in a 400 mega spectrometer, carbon will be about 100 megahertz, 15N will be about 10 megahertz, and so on and so forth. Another important thing is that you can see that gamma for few nuclei positive and there are few nuclei they are negative, right? So as I told, we'll not see any difference as far as NMR spectrum is concerned. It will look exactly the same. The only thing is that the precision frequency, the sense of precision is going to be opposite if you have a negative gamma. That's it. Nothing else, because obviously these are vector quantities. So if this is negative, then it changes. The last thing we did last time is that Zeeman splitting, and that is coming because of another effect of this magnetic moment interacting with this B, and this is the interaction energy. We have devised this particular thing. So obviously, for given for different M values, we have different orientations or given a particular Z component. So this black line is along the Z, and obviously the higher the M, if you have the high M, because of this negative sign, higher the M, more aligned the mu and T, because MH cross is the alignment. So higher M means more longer Z component. Longer Z component will only come when this vector is closer to the Z axis. So therefore, higher the M, more aligned the mu is, and so lower is the energy. So we know that when a magnet aligns to the magnetic field, the energy is the minimal. That is why it is aligned, right? But here it cannot align actually exactly. Quantum mechanics doesn't allow that. But well, the larger the M, that particular thing is there. And for M half, like spin half, we have M is equal to half and minus half, these two, correct? This minus half is called the beta state. It is often written in this way, or often also written in this way down. There is another way. In few books I have seen it is written as D as well, like down, and this one is up. Yes, up. So there are different ways you can say this, but eventually they are basically these two states, and they have this delta E, the difference between them. I can simply plug in value of half and minus half and take a difference between them. That is exactly I've done, and it is coming like this, omega 0 h cross. So we have finished here. Now we have got this. What to do next? The question is, I have got a spin which is precessing at some defined frequency called the Larmor frequency, and we have two states like this. So what we get out of it? One thing we can do is that we can surely tell that, well, I can see from here this expression that given a particular B, as the gamma is dictating what Larmor frequency is going to be. So let's measure this Larmor frequency. Fine, we measure the Larmor frequency somehow. How to measure, I'll tell you, but I measure it. What information I'm going to get out of it? I'll get gamma, because B is known for the spectrometer, so I'll get gamma directly. And this gamma, I can put it back here, right? Close to which, and then I said, okay, we have this nucleus. But that is not something really lucrative, isn't it? Suppose you have the molecule, say CH4, and then you do it, and you said, okay, after a lot of doing thing, you have, okay, proton is there, carbon is there. Well, that can be done from CH analysis. That you don't really need a lot of NMR for that. So the thing is that what's the purpose of NMR? That I'll be slowly coming, and then that will come from the idea that each proton are not going to precess exactly which omega 0, right? But before going that, I'm coming to this Larmor frequency, sorry, the chemical shift. But before going that, there is another problem that you have to encounter. The idea is that we can measure this particular thing very nicely when you have only one particular nucleus. And how? Let me see this. So we have this precision going on. I have this precision going on for this particular thing, and then this is going on like this, right? So what I do is that, as this is a magnet, so a mu, this is actually a magnet, tiny magnet. So what we can do is that I can check the XY plane. I can check this XY plane here, and this XY plane will have its component. right? So this is basically the X and Y component. This component is also going to rotate along with this particular precession. So as this particular thing is precessing, this particular thing is rotating as well. But the Z component, this is the Z component is fixed, correct? It is not moving from there. Only the XY component, or either X or the Y, that means the transverse component, is actually rotating. So generally how it is done is that we can keep a coil. Suppose I keep a coil, and this coil, basically the sample is inside this coil, but I cannot really draw that way. So generally I keep a coil. And what happens that if I have a magnet that is moving in the vicinity of a coil, what happens? It is a Lenge's law, correct? So as it is moving, it will induce an EMF, and that EMF is going to be measured. That EMF can be measured. I can connect this to a computer, and this computer can actually measure this particular EMF if we do this. So how it will happen? Suppose I start from here. So this, when this particular thing is in this region, then suppose I have this nice things. I start from here, correct, at the maximum. Then when this point has gone up to, say, in the 90-degree one, this will go down, because this orientation is different now with respect to this coil. So as it is moving, it will go down. So it will be going down somewhere, correct? Then it is going to come this side exactly opposite. So it is now exactly opposite. So that will go somewhere here. So if it was 1, then it's going to be -1, and then it will come back, and then it will go back to 1 again, when this will come back one full cycle, and this will keep on repeating. So therefore, this voltage that is going to be induced on this particular coil is going to be having some signal, very feeble, small signal, because this magnet itself is not a big bar magnet. It is just a tiny magnet coming out of one single nucleus. But nonetheless, if you have a very sensitive coil, this coil can detect that a voltage is fluctuating with certain nice manner. It is going up and down, up and down. And the frequency, if we just have this particular thing, if I just draw it, if I just draw this, this is going to be something like this, go up and down like this. And this frequency is, what frequency is going to be? This frequency is going to be exactly ω0. This ω0 is going to be the Larmor frequency. So then we have got a very nice idea, very simple. All I need to do is that I have to simply keep a magnet, and then no cost at all. I just keep a simple solenoid, and then let this particular Larmor frequency be happening inside. And as it is happening, it is going to induce a particular EMF, and I measure it. Right? I simply check this. But the life is not that simple. It is not going to do this way. The reason is that we do not have a single molecule. This NMR is not a single molecule spectroscopy. So what will happen? Suppose I have this particular copy of this molecule. Let's take any molecule, say CH4, I can take again. So I have different copies of this. So this is basically different copies of this particular molecule inside this sample thing everywhere. And everywhere this H is present, correct? All these H's are present. And all this H, each is giving four H's, where all is equivalent. All these are going to have, each of these H is going to have a mu like this. So each one is having this magnetic, because everybody has a nucleus, a proton. So therefore we have this mu for everyone. Now all these together, how this picture will look like? The picture will be very frustrating actually. How the picture will look like is, so this is your B, and you have this nice circle on which it was rotating. However, now you have a lot of them, each coming from one molecule, a bunch of them. Is it just going to be like this? No, it is going to be even worse, because few of them are going to be in the alpha state and few of them will be in the beta state. That particular thing I'll be taking up later on. But even, for example, you take the simple case that all of them in a particular state, they are all now, suppose they are all rotating. They are all rotating in the same direction and the same speed. What happens is that they're all Z components are given. The Z components is this much. Everybody has a Z component, which is a big Z component. However, the XY component, which was supposed to be on this particular thing, this XY component are everywhere because they are rotating everywhere, correct? But the Z component is not moving. It is not rotating. Z component is not doing any Larmor precision. So we cannot measure it. The only thing which was earlier doing is basically the X or Y components. But now as there's too many, the X and Y components are spread over the entire XY plane. And as a result, it is zero. It's just vector addition, it is zero. So the situation is that I have now a collective big Z component that does not precess and no X or Y component. So it means it's a static situation, right? That is what we are getting out of the sample tube, because we do not have one single molecule. We have a collection of molecules. So now we have a problem. But the thing is that we'll do something to get rid of this. But before that, this is not the only single problem. We have another big problem. And the big problem is that not everybody is going to be aligned to the alpha state. There will be a lot of people who will be aligned to the beta state as well. So as a result, you'll be getting another circle like this, where these ones are going to be like that. So you have, suppose if you have 10,000, few of them will be alpha state, will be beta state, and then all the XY component will be zero. But these Z components are actually the opposite direction. These Z components are in this direction, right? I had one Z component this direction, another component Z direction. So therefore, these two Z components will cancel each other now. So we are in a really big trouble. So what I see is, already we have no XY component. They have already cancelled because this is fanning around and there is no correlation between them, correct? On top of that, the Z component is also going to be cancelling. So ultimately, if I take the whole sample tube, I have no magnetization left because I cannot see the individual nuclei. I have to see collectively, and the collectively nothing is coming. So is NMR going to fail? Luckily, no, because between this alpha and the beta state, we can see that there is a small energy difference, correct? The energy difference is very small. I'll give you a few numbers today. We'll see that how tiny that particular thing is. But nonetheless, we have energy difference between this. And then we know that in a normal situation, nature always prefer to go to the lower energy. So that means we have a little more into the alpha state, which is the aligned one, correct? We have this aligned one, alpha state, than the beta state. So number of spin are going to be, so what do we number spin? So that means, for example, this is molecule 1, this is molecule 2, this is molecule 3, this is 4. Maybe so suppose this one is the 1, then maybe the 2 has somehow come here, then maybe the 3 is also coming here, and 4 has there, like this. Which one will go in which state doesn't matter, it's completely random. But number wise, as this particular state is a slightly lower state, so the number of n, if I just call it n of alpha is going to be slightly larger than n of beta, because of this is nature's idea. This is actually going to be a Boltzmann distribution, and in the Boltzmann distribution that happens. As a result, we will be having slightly longer vector here than there, and as a result, we have a tiny amount, tiny amount of magnetization in the effective magnetization left. So out of this entire thing that we have done, we have millions and millions of molecules, but ultimately we get a small effective Z direction magnet, which is also not moving. Z direction magnet, fine, it's called a bulk magnet. So this is the bulk magnet, it is called. This is called a bulk magnet that is coming from each individual molecule, but it is not moving. It is not doing any Lenoir precision. So that's a problem. But at least we have something. It is not exactly zero, which we thought that it was going to be. Now the question is that how big this particular thing is, right? That I'll be giving you a number. How big this particular number is, this magnet is. Let's have a look, right? Then we'll go forward. That we'll do something that why this is not precessing, but then what to do, we'll do that later on. But let's see how big this number is. For that, I need to help of my notes because those are numbers. I don't remember them. Where are they? Yes, they are here. So as I told, this is going to be a Boltzmann distribution. I hope you have read our Boltzmann distribution. I'll not go deep into it. So n, so you have different m states, correct? So these are two m states. So one is here, m is half and minus half. So different m states. So what will happen is that if I call this nm as the number of particles in the mth state divided by the total number, correct? So you have 10,000, then how many in n half and another with n minus half, that is what I will nm by thing. This is going to be given by this expression. It can be derived, Boltzmann distribution, but it's not necessary here. I'm just going to write it down. And then this is basically the sum of all. It's called the partition function. You don't need to know what exactly that thing is, but just the expression. So this is a fixed, right, our all m. This is called the ratio, right? Okay, the distribution, how this is going to be. Now, if I just take in our simple case n minus half and n half, I'll be taking directly that. So this particular quantity is a constant, correct? So if I just take n minus half divided by n half, that means how many in the beta state versus how many in the alpha state. So clearly this can also be written as n beta or n alpha, correct? And we know that as the beta state is the state which is slightly higher in energy, so the n beta is going to be slightly lower than the n alpha. So this number is expected to be less than 1, correct? But how much it is less than 1? Is it 0.5 or it is 0.7? How much? Because we know that if it is exactly 1, if this particular thing is exactly 1, that means n beta and n alpha exactly equal, then we have equal number here. So that this is going to be 0. So we do not want them to equal. In fact, what we want is that this n beta be as less as possible. That means this particular thing, if it is 0.5, even better, right? Then 0.7, 0.5, then we have a sizable bulk magnet, and then NMR is going to be very sensitive. So let's see how less it is. It will be less than 1. How much less is then? Let's do it. So if we can do one more step, I can write it down this way. So this is going to be exponential minus e minus half or e beta kt divided by exponential minus e of half kt. Correct. So therefore, I'm just writing this one half and minus half here because this part is common. This part is going to be cancelled in a ratio like this. So this is going to be. So I can round this. I write it on this a little more like exponential. I write it down together is minus e minus half minus e half divided by kt or exponential minus delta e over kt. That delta E that I was talking about, the Zeeman splitting delta E. Correct. Now the thing is that generally this delta E with respect to KT, if we just do it, this delta E is going to be extremely small, very small amount of energy difference between them with respect to KT. So this whole thing is going to be much larger, much smaller than 1. I can approximate this as 1 minus delta E over KT. So this is the expression that is going to be the ratio. Let's see how small it is than less than 1 in a real situation. So what a real situation I have taken? I have taken capital T to be 298 K room temperature, and I have taken the B to be 1 Tesla, right? Generally, it is slightly more than 1 Tesla. It is about 10 Tesla, but I have taken in this example this thing. And therefore, I can calculate delta E. Delta E is coming to be something like gamma times B0 H cross. We know that this is the expression. We can put the gamma of proton. This is 2.67, 10 to the power minus 10 to the power 8. Tesla inverse is inverse. Then 1 Tesla I have taken B0, and H cross is 1.05 10 to the minus 34 joule second. Right. So delta E, if I just do it, is coming to very something like 2.8 to the power minus 26 joule. Now you understand how small the delta E is. It's 10 to the power minus 26 joule. That much. That is the tiny amount of energy difference between the alpha state and the beta state in 1 Tesla. Even if you have 10 Tesla, it is going to be minus. Even if you have 10 Tesla, like a 400 mega spectrometer, which we have in NISA, correct? 10 Tesla, and that 10 Tesla will have 10 to the minus 25. Just one will be dropped. Even then, it's going to be extremely small delta E. With respect to KT, it is much smaller. So definitely we can use this thing. Now let's see how much is delta E by KT, because delta E is done. So KT is only doing it. So this is going to be 2.8 10 to the power minus 26 joule, and then I'll be taking the KT, which is K is 1.38 10 to the power minus 23 joule Kelvin, and then I have 298 Kelvin. That is the T, and it turns out to be is equal to something like 6.8 10 to the power minus 6, correct? That is delta E by KT. So obviously I told you that this delta E by KT generally for a normal temperature, room temperature, is extremely small than 1, and it is really smaller than 1. This is really smaller than 1. Fine. So therefore, if I have this, then let me try to find out this 1 minus delta E by KT, this quantity, so that we get this ratio. And then the ratio that is going to come is something like N minus half divided by N half is going to be 1 minus this quantity, and that is going to be 0.9. How many? 1 2 3 4 5 2 3 4 5 3 2. So well, we have got less than 1 as we expected, but it is not 0.5 or it's not something like 0.7. It is 0.9999932. What does it mean? It simply means that if you have 1 crore so let me see how many zeros here. 1 2 3 4 5 6 7. So you have 1 crore total. 2 3 4 5 6 7. These many molecules if you have, then if these are in half state or the alpha state, then the beta state is going to be 9999932. The difference is going to be only 68 in 2 crores. So if you have 2 crore molecules, correct, then you have only 68 molecules which are different between alpha and beta. So basically, eventually, although you have 2 crore molecules in your sample, you have taken a nice, beautiful sample you have taken, you have 2 crore molecules there, but the NMR signal is coming from 68 molecules only, effectively. That is why NMR is so insensitive. That is why in other spectroscopies, for example, you can work with nanomolar range, but in NMR you have to give in milligrams levels. If for carbon-13, which is slightly less sensitive, and particularly carbon-13 is only 1% natural abundant, you need in hundreds of milligrams level. Why? That's because of this reason. Theoretically, I have just proved that why NMR is insensitive. So the bottom line is that NMR is not sensitive spectroscopy. It is not sensitive and it is expensive, right? And yet people are doing it, and we are having a class on this. So there must be some reason behind it, correct? So let's see what the reason behind this, what information we get. In fact, just now we have just told that the information is even very simple. We can get the gamma, because the omega 0 that is coming out, the omega 0, that is simply gamma times the B0. B0 is fixed for a molecule, so therefore gamma, correct? So you can only know. But the good thing is that it is not like that, because we have a nucleus, correct? However, this nucleus is not exact. That nucleus might be having certain gamma, correct? But this nucleus is not actually the only thing which is present. On top of that, we have electron cloud. So this electron cloud, it might be asymmetric, it might be anything, it might be something, doesn't matter. But you have electron cloud, correct? Well, this electron cloud is going to do something, and that is something that is going to be, we'll be calling it a chemical shift. So I'll be giving you the theory, not theory, but a little bit of mathematical reasoning that why chemical shift, where from chemical shift arrives, or where from this particular thing happens. So it's called chemical shift, and that chemical shift is actually going to make NMR very informative, very very nice. So therefore, let's see what chemical shift is all about. We have this electron cloud. However, for understanding easily this particular concept, I'll be assuming as if this electron is making a circular orbit, like a Bohr's orbit about this nucleus. Then you'll understand how this particular thing is happening. So one thing that you must be knowing is that if I have a magnetic field B, and in the vicinity, if you have an electron which is just started moving like V velocity, then if I have a magnetic field and a charged particle is moving, then it experiences a Lorentz force, and that force F is minus Q P cross B. Actually, it is Lorentz force is also Q times E, but I don't have any electric field here, so I'm just dropping this. Minus Q V cross B. Now the idea is that let's take this the direction of the B. So B is suppose like this. That means it is exactly from top to bottom going through the paper, right? Now, if we have this, then what is the, so that you have this particular thing V cross B, but then you have a minus because it is a negative charge. So therefore, the V cross B, the moment it starts, rotating, rotating, it will be like something like this. We have this nucleus, some plus charge, plus Z. You have an electron that has started moving, V, right? And then B is already in this direction, and therefore the V cross B is actually V cross B is this direction. However, because it is negative, it is going to be this direction, because it is negative, minus Q V cross B. So this will be immediately it is going to be having a force like this. So it was trying to go this direction, but there is a force in this direction, so it will actually go in the middle direction. And eventually what will happen is that it will actually go in a circle. So this is the V that is talking about. This is the B, and this is the center, which is the nucleus is there, and the force, the Lorentz force, is going to be directly towards it. And then in each position it is going to be towards the center. So therefore it is actually going to move in a circle. Now imagine that an electron is moving in this particular direction. So if it is moving in this direction, then the current is actually moving. There is a current Q, current I, let me do I, that is the current. So as this electron is moving in this direction because of the V and Lorentz force, and I is going, so this current is going down. And now we know that if the current is going in this direction, V cross B this, minus V, and I is going this, and then the magnetic field is going to be, am I doing something wrong? V in this direction. So This is moving this direction. Oh, V cross B was the opposite direction probably. V cross B. Ah, okay. Yeah. So sorry, we have to if we have to have this particular direction of the force, the B has to be opposite. I just drawn it wrong. So this direction, the B is not going to be the opposite. So therefore, it's going to be your B has to be in this direction. That means it is pointing up. Then only if you have a pointing up like this, then the force is originally like this, V cross B, and then it's opposite exactly. So if you have this direction, that means it is coming out of this plane, and then you have this, but exact everything is same, that the original B is coming out of the lane. Then only this picture will be there, and the current is this direction. And if we have a current on this particular direction, current is moving, then that will create a tiny magnetic field at the center, obviously, because we know any current loop creates a magnetic field, and that magnetic field is going to be exactly opposite. So this tiny magnetic field, which is coming from BE, because of electrons movement, it is going to be in the opposite direction. So therefore, we had an original B, correct? Original B, that B0, that was in this direction. That means it is pointing up. But the actual BE, that is in the opposite direction. So they are canceling, right? So therefore, the effective B is going to be slightly less. So this is why in fact, there are many places that is being asked that why electron being paramagnetic, it is giving a diamagnetic effect. Diamagnetic means it is opposing the original field. So the created magnetic field is opposing the original field. One was coming out of the plane, and this one is going into the plane, exactly opposite. This is happening. That's because you have this motion in like this, right? This negative charge. So now this B effective is, now the question is that this B effective can also be written, this B effective, this B1, BE, this can be written as a proportional sigma into the B original B0. Why? That's because the larger the original B0, greater is the force, and the greater the force is, the tighter is going to be the circle, is going to be a smaller circle, and then the current will be more, and then the effect will be more. So these are all connected. So therefore, the B effective, which is the opposing field, is going to be the proportional to the B0. So as a result, we often write that omega 0 is actually gamma times B effective, because the nucleus is not seeing the entire B0, but it's effective screened one, and that is gamma times some 1 minus sigma times B0. This expression is used for chemical shift. So therefore, this 1 minus sigma, that is because 1 B0 minus sigma B0, because BE is proportional to that. And this is called the chemical shift. Because the thing is that why it is chemical shift? Because the moment I have changed from B to be effective, the position is going to change a little bit. Earlier, if I have a situation like we have, this is the thing, and this is your omega 0, then it will shift a little bit to a different place if depending upon a 1 minus sigma, or depending upon the sigma. So therefore, this shift is coming from the original Larmor frequency because of the chemical shift, and that is coming from this electrons, right? Although electron is in the cloud, but we have just drawn this way. The movement of these electrons are creating a field which is opposing the original field, and that is the effect, the theory behind this chemical shift. So as the plan was that all these things, that chemical shift, kept coupling, then everything you will encounter again later on in this entire course, but more on to chemistry and biology point of view, correct? The reason behind the chemical shift will never be discussed after this 5 classes. So because this the theoretical part, the optional theoretical part is to your understanding where from these things are coming, where from the chemical, why this NMR is insensitive, why we need a lot of sample, where from the chemical shifts are coming, all these things. So I hope you are understanding this thing. If you not, please tell me if you have any concept. But the idea is the charge particle, being negative charge particle, is moving, and that movement around the nucleus is creating a tiny magnetic field. Because of this, the movement is creating a current, and that current is creating a tiny magnetic field, and that is the concept of sigma. So now you can imagine, now once this is done, we can go back to this thing, that if I have two different nucleus, if I have two different nucleus, like one is like this, another two different nucleus, and in one situation I have this is the cloud, another one I have this cloud is really dense, right? This cloud is really dense. So in one case, I have slightly lighter cloud and the dense cloud. So obviously, if I have dense cloud, that means you have a lot of electron cloud surrounding this nucleus. Obviously, what happens that this effect, this amount of BE that is going to be created is going to be more. And that is why the screening is also going to be a much larger screening. So that is why as the screening is going to be higher and higher, we can have the position is different. So therefore, the positions are going to be now depending on the screening or the chemical shift, and that is something that then we'll know that which particular type has a different type of chemical shape. Those things will come eventually, but as far as our discussion is there, this is how the chemical shift originates. So okay, we have understood one thing, that NMR is not that bad, correct? Because this chemical shift is going to give us not only the information about which type of molecule or which type of atom is there, whether it's a proton or carbon or nitrogen, that is there. On top of that, we can see that which type of screening is there. So obviously, protons with aromatic in an aromatic ring is going to be a slightly different environment rather than in the aliphatic one. So we can differentiate between them as well. And if we create a chart that, okay, the aromatic protons have this frequency, the aliphatic protons have this frequency, then we using that chart, I can do a little more than just knowing which type of nuclei it is there. Very good. We can have, but let's come back to the problem that we had. The problem is that it is not sensitive. That is problem number one. Fine, but even then, if we accept this particular bulk magnet, which is a tiny bulk magnet we have got, 68 in 2 crore, correct? But that bulk magnet, we can, okay, fine, I have enough engineering skill, I can make a super sensitive coil, I can do it. But this is a bulk magnet which is along the Z direction, it is not along the X or Y direction, it is not rotating at all. So if it is not rotating, then how can I even measure the rotation speed? Forget about chemical shift, I cannot do anything. So for that, I need to first tip this particular bulk magnet, not the single magnet, the bulk magnet out of the Z axis to the XY plane. And if I can do this, that if at any point of time, this particular bulk magnet, instead of Z direction, points towards the X direction, like this, a small one, let it be a small one, but now it is at least pointing in the XY direction, then this XY direction, what will happen? It will start rotating again, and then I can measure it, and that is exactly is done. And this rotation from Z, the bulk magnet from Z axis to the XY plane, so that we can measure it, is done by radio frequency pulsing. That is why we give radio frequency pulsing. So radio frequency pulsing. Now, to be very frank, if I really want to do the theory of radio frequency pulsing, that's going to be unfair. This course is probably not for going to that deep into the thing. So the theory part, that how radio frequency waves interact with the nuclear spins and what's happening, is that is something I'm not going to do here. It is, and also it is not doable in 3 or 4 classes. It takes a lot of time. When I take a full course on NMR, I explain that theoretically with quantum mechanics and slowly. I cannot do that now, but I can tell you that what effect it will create. That much I can tell you. That what happens is that we have a situation. We have a situation that we have this particular direction B, and each individual, although we have the bulk magnet, but each individual one is actually rotating in this particular fashion, correct? Each individual rotating in this fashion. Although we have a very tiny amount of Z magnet in this particular tiny amount of Z magnet here, correct? We have a very small amount of Z magnet, but nonetheless, this single one is doing. So what we do is that we use a coil and this is a RF coil. It's called RF coil. And this RF coil is basically theoretically what it is, that if you have an RF coil like this, right, and if you just put some current through it, and we know that if the current goes through a coil, magnetic field is getting created, correct? And the magnetic fields are generally straight in the middle part, but then they go like this. You can see something like this, correct? So the idea is that the middle portion is having this lines of force almost straight. That means you have a very uniform magnetic field in the middle. But then if I now change the current, that this current is in particular direction is going, then this magnetic field is like this. If you switch the current, then what will happen is that if the now current instead of this direction, if you current in the other direction, then the magnetic field lines force will be nearly the same. Only thing is that now they will be starting into the opposite direction. So there now the magnetic field is going to be changing to opposite direction. So therefore, in this particular middle portion, which is basically a straight line, when the current is in particular direction, then the magnetic fields are something like, suppose like this. But then when the current is changing its direction, then the magnetic field current is something like this. And if the magnetic field, if the current is zero, then your magnetic field is zero. So now imagine I have a current which I'm creating like this, like an alternating current, AC current. Then what will happen? The magnetic field inside this coil is also going to follow exactly the same thing, same particular frequency, correct? And it is going to be an oscillating current in the XY direction. So therefore, it is going to be in this particular place. It is going to be an oscillating current into the straight line direction, and that is done in the XY plane. So that particular current is given in this XY plane, correct? So therefore, I can at least mathematically I can write it down that the BAC, I only write this much, no more theory than this. The alternating current BAC, the RF coil, the pulsing that is going to be giving, is something B1 is the magnitude and cos some omega 1 t, correct? And it is going to be, or omega AC actually, omega AC actually, and then this is going to be in the X direction or Y direction. This particular thing is there. But then what happens is that original spins, they are having rotating like this. So a field like this doesn't really do the act. But however, Professor Hosur was also telling the other day that even if I have a field like this, which is rotating into the XY direction like this, any linear field like this can be thought of having a two counter rotating fields. One is rotating in this direction, another is rotating in this direction, right? This direction, so that the Y components are always canceling each other. Y components are also canceling, and X component goes from maximum to 0 to 0, then goes to like this. So therefore, actually a linear field like this, which is going up and down into the XY direction as it is done by this solenoid and actually done inside the magnetic field, is thought to be one is rotating in this direction, another is rotating opposite direction. Now, any one of them is going to match with the rotation of this particular sense of rotation, and that will actually give you the energy. The other one is going to be wasted. But nonetheless, it will only happen if omega AC is equal to omega 0, or omega 0, not only omega 0, but with the chemical shift. So this condition has to be there. That means the frequency at which this linear field will be fluctuating, but this particular current is fluctuating, that should match with the Larmor frequency. And this particular condition is called the resonance condition. I'll be not talking many more on this. So this resonance, NMR, the R is resonance, and I at least had to tell this thing. So nuclear magnetism, we have understood nuclear magnetism, magnetic moment, Larmor precision, Zeeman splitting, everything is fine. The only thing which was left over in NMR was the R. Where from this R is coming? So the R is coming from the RF part, and RF part is necessary because otherwise this tiny bulk magnet, this particular thing is along the Z direction, it is not rotating, so we cannot do anything. But then once this particular AC current frequency is matching exactly with the Larmor frequency, that is called the resonance condition. And mathematically, it can be shown that I cannot show here, that if we do that, then the effect that will happen is that this particular magnet will slowly start tipping from the z direction to the xy plane, like you have just flip it, right? And the flip it, and then that is going to be this particular equation. It is going to be so it will be flipped like this, and then the time it will take and the rotation is going to be given by this omega 1, which is basically gamma times b1, and this b1 is basically this b1, which is the field. So therefore you have an oscillation frequency, but you have to have a magnetic field. What is the amplitude of this tiny magnet which is created by this? That is b1, and this b1, if it is gamma times b1 is omega 1, then omega 1 tau p is the pulse length. That is why it's called pulse. It is switched on and for some time and then off. During that time, this pi by 2 is measured 90 degree. So if I can make this, that I create this whole thing, I create this whole current thing for just small amount of time, 10 microseconds, during which this bulk magnet is going to start tipping and come to the xy plane, and I have to switch it off, because if you do not switch off the RF coil by that time, it will happen all the way and come back to the negative direction, and then it will be the same problem. Earlier it was positive z direction, now it is negative z direction. That is not necessary. So I have to simply switch it off as the moment it is coming into the xy plane, and that is called a 90-degree pulse. This is what generally you will be seeing many times later on, maybe in the course. It's called a 90-degree RF pulse. Simply means that you are switching on the pulse exactly that much amount of time that omega 1 tau p, this product, is equal to 90 degree, so that this bulk magnetization is tipping. And once it is tipped into the xy plane, it will start precessing again with the same frequency. Each one will have its own frequency according to its chemical shift, how much it is seeing the electron cloud. And then once that is there, you can actually keep another coil, which is basically, this coil is RF coil, but you can actually keep a detection coil, which I have already proved here. In a detection coil, yeah, you can have a detection coil, and this detection coil, once this, now earlier it was just one single component, but now it's going to be, now I can modify it, like this is going to be a small bulk magnetization, but that is also rotating like this, and that will create an fin, and everything else is going to be the same. So we can find this omega 0, which is effectively gamma times 1 minus sigma times B0. Right? And this, depending upon the sigma, this omega 0 will be at different places, and we can see this. So this is in a nutshell the concept of NMR spectroscopy. This is how NMR spectroscopy is done. Now, anything beyond this is second tier. So very second tier. So it is really I can talk about many things from next class. I have another 3 classes, so I plan to make this as per the requests from the students. So this is, you want anything you want a little more, like for example, how this particular you want a theoretical description of say how this particular thing is happening, how it is tipping, I can tell that one class. Or you want that, okay fine, I have understood that thing, you talk a little bit about other things like what do you mean by 1D NMR, 2D NMR, what is D there, I can talk about that as well, any other theoretical thing. So I have taken 3 classes to briefly go through the entire mechanism, what NMR happens, and now I really want the participants to tell me in which direction you need to know a little more theoretically, and then that direction I'll be going. Otherwise, I'll stop here and then I'll take questions.
Okay, thank you, Dr. Ghosh.
Yeah.
Audible? Yeah. So participants, your questions, please. You can type actually. You can type in. It is come to that whether it is been connected or not. You should see these. Hello, participants. You can put your. You can type your queries in the chat box. You can type your questions in the chat box, or you can maybe speak out. You can unmute your mic and speak out. একটু দেখো তোরা কোথায় আছে। Yes, come.
हाँ काम हो गया। अब थोड़ा वो कैसे स्टूडेंट को इंटरेक्शन में लाने का।
How to make them interact. करो तो।
नहीं बेटी बेटी
इधर बैठ।
यस
Yes, participants, your response please. Any question or any clarification? चैट बॉक्स में कुछ है क्या?
नो क्वेश्चंस।
So no questions. Anyone? No. Okay.
What is this? Because what is this?
What is that? Can you clarify what is this channel? What channel you are talking about? Who is he? One participant has written, what is this channel?
What's channel? What is the channel?
Someone has written, can the participant clarify it? What channel, what is your confusion?
On YouTube. Wait, what is the channel?
What channel you talking about?
I could not, it's not
You
clear.
have drawn that, I think, the circuit, na? When you are showing the current is flowing and all the magnetic field is generated, I think that is the channel only. I think.
No, something Japanese symbol is also coming. I don't know. If you can write little more explicitly with your name, please. Okay, I think it's not clear to us. And any other participant? Anyone is having any question? Then one more thing, as Professor Ghosh was asking you, okay, which way you need this? You need more theoretical aspects, or you want to have some idea about 2D NMR or some kind of things. So if you can kindly.
So 2D NMR is going to be discussed later on in detail, but I believe that is going to be only
some preliminary ideas. Some preliminary ideas you can get at the beginning.
Yeah. So basically, those who are going to be more onto the application of like different COSI, NOSI, etc., that's going to be as we have planned the course. But what I was talking about is that what do you mean by D? How that this 2-dimension is coming? What a little more onto things we can discuss, or otherwise I can discuss into something like relaxation, like block equation. So these are going to be slightly more in depth. The very basic thing is about 3 classes it takes, and it took 3 classes. This is how NMR is primarily done. Anything more than you need?
One response has come. Is one person, Vijay Kumar. He writes, while we are applying the same in 2D, at that time we may need some clarifications. Okay, that time I think we will be covering this 2D part. I think he will give some clarification. But beforehand, if you like, then Professor Ghosh can take a part of it briefly. Okay. So if you can write to him, his email ID last talk he has given his email ID. Otherwise we can share his email ID with you. So you can write directly to him. Is it okay, Dr. Ghosh, now, Professor Ghosh?
Yeah, sure.
You can directly write to Professor Ghosh, whatever way you need. Okay? So that will be easier for him to plan the next lectures.
Otherwise, I'll do something, what I think is next, like a little bit of relaxation and other things I can do.
Hello, sir. Professor Ghosh, one person has actually requested you can provide a overview related to 2D NMR. So a small part you can cover maybe. That will be better.
I can give a little bit of idea that how these 2D pictures are going to be coming up. Like for example, later on, you will be seeing that if we have a 2D spectrum, you will interpret it. Interpretation is different than exactly how these pictures are generated. I can talk a little bit about that background of this.
That will be nice. So that part you can keep in mind.
Yeah,
and Dr.
I can do that.
Ghosh is trying to tell something.
Yeah, Professor Ghosh, I am Sumit Ghosh. See, I'll be taking this next after your classes, na. So I think if you can tell about the little bit about the anisotropy, the physics part of anisotropy effect, na.
You mean the chemical state anisotropy?
Yes, physics part of that. If you can give little bit specifically the single bond anisotropy, like single bond benzene is more, it is very little bit easy to understand compared to that. Na, many students have a doubt on the single bond anisotropy effect.
Okay.
Just the physics part, na, because there is a lot. Again, there is a electron movement, and that creates the magnetic field and how it is affecting. Na.
So basically, what you are talking, the ring currents are those things you are talking about?
Yeah, so the ring current also you can cover the whole anisotropy effect in NMR, na? How it depends on the various space, na? How it differs depending on the orientation of the molecule in the magnetic field. Na?
But in liquid state, you will be having more.
Because later on we have this solution state also, na? Sorry, solid state also, na? So if you give little bit of one lecture, you can devote on that. Maybe next lecture or maybe next week, na?
Fine, okay.
The physics of the anisotropy.
Okay, fine, no problem. Sure.
Physics of the magnetic anisotropy. Na? I think many people will be interested, specifically when the solid state will come. Na? Solution, it will have little use, but solid state it will have more use.
Yeah, of course. Yeah, dipolar interactions and those things will be.
Yeah, that's why. Yes, dipolar interaction. That's why. So maybe next week also you can. Okay. That is from my side, from the.
So tomorrow, so as this student has talked about
you can go
2D. So tomorrow I can talk a little bit about basic of 2D. That how this 2D is theoretically is how this is physics wise how it is working in a 2D.
Yeah.
And then next week I can talk about this. Yeah, that's no problem. Right. Yeah.
So that will give some preliminary idea so that they can follow the later part easily. I hope so. Okay. So accordingly, you plan, and from your experience, you feel which way best these students can be prepared for the higher part of the course.
Yeah. Another thing, that last thing I was talking about, that they probably, if I talk a little bit about the longitudinal and transverse relaxation, the T1 and T2, that is very important for
relaxation part.
People.
That also you can introduce. That will also be very useful.
Yeah. So relaxation like block equation and T1, T2 like inversion recovery, how this measured, those things.
Yes.
They will be having this thing. T1 and T2 later on also.
Idea they will have so that they can enter into the topic better way.
Okay, so let's do that way. One day I'll be talking about a little bit of 2D, another than relaxation, another than anisotropy.
Okay, that will be nice, sir. Yeah.
Okay. Fine. No problem.
Okay. Then.
Okay.
Participants, we can stop it here. So you can directly communicate with Professor Ghosh, whatever your doubt is. Okay. And we will be sharing his email ID once again. Okay. Thank you, Professor Ghosh. Thank you very much.
Yeah. Okay. Bye.
Thanks a lot. Bye.
Sure.
Professor Ghosh.
Yeah.
Disconnected. I think tomorrow our class is at 5:30, right?
5:30. Yes.
It's okay, now. Because
Why have you changed the time, by the way?
time, one more course is going on. So
Oh,
there
okay,
are some
okay.
common
Fine, fine,
participants, so they may miss it. So for that reason, we have shifted
No
one
problem.
class.
5:30 is fine. 5:30 is fine.
I
No
know.
problem.
Okay, thank you very much. Okay, then.
Yeah.
Okay, fine. ओके थैंक यू कुछ कर दो कल 6:30 तक है हमारा मालूम है ना 6:30 मतलब 6:40 तक जाएगा
चलो दिल्ली पे चलो
कल प्रिपेयर होके आना लेट जाना
दिल्ली पे चलो
बस ओके
चलो
थैंक यू रोहित